Right, welcome to our last of the semester. Okay. So obviously a few topics that we want to talk about, but we already discussed the first three roughly last class, and so we have a few things to go over here. If I can't, I'll post a little supplementary video for anything that I don't cover in the class itself. But before I do, let me just talk briefly about test 3. We released latest by Tuesday, midnight. If possible, I'll try to release it earlier so that you have a little bit more time to work on it. Once again, just like the last two, you'll have about 48 hours to work on it and submit by a grade scope. I do want to point this out. For some reason, a couple of you turned in the test a little later than allowed. I was still a little bit lenient, but this time I won't be. So please make sure you turn in your test before the deadline. Okay. Unless you have pre-arranged with me for whatever reason, there are some people who have had some issues and had to travel back. So they may get an extension or a late submission allowed, but otherwise you're not. So what about the material on the course? Well, the long answer questions will focus on diffraction, essentially everything after the test 2, basically. But for the short answer, expect that you may get a question, you may get a few questions from the first part of the course, first 2 parts of the course. Basically conceptual mostly, but you may have a little, numerical little thing to sort out or something like that. So that's the breakdown of the material on the course. But long answers will all be from the diffraction part of the course. And I don't know how much interest there is in having this, but I can hold a review or Q&A session on Wednesday, December 13th via Zoom at this class time, 1 o'clock, if there is any interest. Maybe I can send out a survey just to gauge the interest level or something. And then if you're interested, then I'll hold this review/Q&A session at this time next Wednesday. Okay, any questions about test 3 so far? All right. If not, let me also remind you that the teaching surveys are open for this class, 1361. And for those of you who are in my 1661 writing section as well, it's open for you as well. Currently, the responses are pretty anemic. It's only like 5 out of 21 in this course. And even worse for the 1661, only 1 out of 16. So I request you to please take a little bit of time. Don't expect that your friends are doing it, so you don't have to do it, because basically nobody has done it. So as I mentioned already to you, how much I value the feedback and how I've used it to improve both 1361 as well as 1661. I've changed a lot of things in 1661 as well, by the way. It's not how traditionally this course was taught previously, so I'm hoping to get some more feedback from you to keep improving that course as well. End of the survey period is December 10th, so please, so that's before finals week, so please get it done before then if you can. I really appreciate it. Thank you. Okay, so let's get through the material today. So we already discussed Fresnel diffraction at a circular aperture. We have these Fresnel zones that came about from the Fresnel half-period construction. And as we saw, like if there are if the M zones are inside this aperture, and if M is even, then each zone cancels with its adjacent one, the odd and the even, odd and even, they cancel with each other. So the total electric field will be 0 at this point P of observation. If M is odd, now one of the zones is not canceled, so you'll get a bright spot. Okay, and so that, and if you remember, the unobstructed wavefront by itself is on the order of E1 over 2. Okay, and therefore we can get, in fact, 4 times the intensity. If the M is odd compared to the intensity when there's no aperture, when there's no obstruction with the aperture. And this is just a reminder, this is how the vibration curve looks. This is for any general point A in the aperture. For example, this one over here might correspond to that point A on the vibration curve. And then as A increases, it might enclose 1 Fresnel zone, and then it might enclose 2, which would be down here, which would be a minimum, so on and so forth. And you can see when you just have the unobstructed wavefront, which is from OS to OS prime, the phasor is half of the phasor from OS up to ZS1, which is the first Fresnel zone. Okay, and to compute how many zones are enclosed inside the aperture, we can use something called the Fresnel number, which corresponds to roughly the radius of the aperture, r, pi r squared. That's the area of the aperture divided by the area basically of a Fresnel zone. And I did this in the supplementary video, the math for this in the supplementary video that is on your module, and so that you get this result. So that tells you how many Fresnel zones are enclosed by an aperture of certain radius r at a distance where r rho is the distance, of course, from the source, and r naught is the distance from the aperture to the observation point. And I also did in that supplementary video a little example where I said, suppose rho goes to infinity, so you have plane waves coming in rather than spherical waves. Then when rho goes to infinity, you're just left with r squared by r naught lambda, basically. And you can look at that derivation to see how that comes about. Okay. All right. And let's see. Okay, anything else I wanted to say here on apertures? No. So then we can also talk about something else, which is like the complement to an aperture is an obstacle. So now we have not a screen with a hole in it, but instead a ball bearing or a circular aperture or circular obstacle, a disc, etc. All of these are circular obstacles. So as we've already talked about, the unobstructed wave has the amplitude. We mentioned this several times. E equals the amplitude from the first Fresnel zone divided by 2. So if a circular obstacle just covers that first Fresnel zone, then the amplitude of the electric field is the amplitude from the unobstructed from the first Fresnel zone minus the amplitude from the first Fresnel zone. Is the unobstructed wavefront minus the amplitude from the first Fresnel zone, because that's mod E1 is the amplitude from the first Fresnel zone. So a circular obstacle which just covers the first Fresnel zone can end up having an electric field which is minus E1 over 2, which is almost the same as the unobstructed wave, right? Except for the minus sign. So the intensity at the central point of an obstacle, the shadow in the shadow region of the obstacle, the intensity can be as bright as the unobstructed wavefront itself. So what we are predicting from this theory is that there can be a bright spot at the center of the shadow of an obstacle. And so let's just show you the proof. So here is a ball bearing which has been illuminated by plane waves from a laser beam. Of course, you see all the fringes in the region outside of the obstacle, but right at the center point, you observe a bright spot. Okay. And this is very interesting. This spot is called the Poisson spot. And why it's called the Poisson spot has a funny story, which is actually when Fresnel first published his theory, he actually submitted it for a prize, which was judged by Poisson. Okay, Poisson, as you might know, Poisson equation, he's a very famous Poisson conjecture, etc. So there are many famous results in his name. So he did not believe in the wave theory of light, by the way. Okay. And so he said, this theory is nonsense. I'm going to disprove it. And he took Fresnel's theory and he made this prediction that at the central point of an obstacle in the shadow region, where if you illuminate with light, there will be a bright spot. And he said that that's nonsense. There's no such bright spot. We don't observe it. So therefore, this is nonsense. So this wave theory is disproved. Unfortunately for him, Arago said, well, what if I do the experiment? So really, this spot should have been named the Arago spot, not the Poisson spot, because Poisson actually didn't believe in his own prediction. But Arago, when he did the experiment, observed the bright spot, and this, of course, vindicated Fresnel and the wave theory of light and all that. But the long story is Poisson has his name on this particular prediction, even though it's Arago who should get the credit for actually doing the experiment and observing. Well, anyway, so that's the story of the Poisson spot. And if you want to understand it with the vibration curve, you can. So imagine now the point A, which is now at some arbitrary point, not necessarily at the first Fresnel zone. Of course, if it's at the first Fresnel zone, the point would be over here, basically. That point would be at this point over here. That would be the point of the first. So if the obstacle was exactly the size of the first Fresnel zone, then the phasor, now, of course, OS prime is the unobstructed point. So this is, remember, this is like the opposite situation to earlier where we had an aperture. Instead, now the opening starts at the point A and goes out to infinity, right? Which would be the unobstructed point OS prime, which is at the center of this vibration. So the phasor goes from AS up to this point OS prime. And of course, now again, when it goes to the first Fresnel zone, that will be the size of this phasor. And that's, of course, as we just said, can be bright. Okay. You can see it's in the opposite direction to the point from going from here to here, which is the aperture phasor. Okay, so it's 180 degrees out of phase with that one, as predicted. Okay, so that is in just the vibration curve result, nothing very special. It's hopefully obvious to you that should be the phasor. Okay, what about these Fresnel zone radii? We've already discussed one way to derive them, which is using the Fresnel number. But now I want to show you a much simpler derivation of the Fresnel zone radii, which is to tell you how many Fresnel zones are there in an aperture of a certain radius. And the way to understand that is we know how the Fresnel zones are constructed. We take the distance P to R naught, which is the distance from P to the aperture central point. And then we take another sphere with radius R naught plus N or M being the mth zone or nth zone, Fresnel zone. We take another radius or sphere of radius R, small rn equals R naught plus N lambda over 2. So the nth Fresnel zone, again, is every adjacent zone is out of phase by a period pi, by a phase difference pi. So this one, nth zone, will be out of phase by N times pi or N times lambda over 2. So that's the distance. So the intersection of these two, of this one, is where the nth Fresnel zone is located. Well, as you can probably tell from this construction, we can immediately calculate from this Pythagoras theorem in this triangle that Rn, the radius of the nth Fresnel zone, is simply using Pythagoras theorem on this triangle is just R naught plus N lambda over 2 whole squared minus R naught squared. Okay, so just expand this, and subtract out the R naught squared cancels. Then you're left with a term which is N lambda times R naught plus a term which is N lambda over 2 the whole square. And that term is much smaller than N lambda naught times R naught. So therefore, Rn can be approximately written as N times R naught times lambda. Okay, so that is in fact the same result that we got from the Fresnel number. So if you go back and look at the example I worked out in the last part, or you look at the number and take the limit when the source is infinitely far away, then you'll indeed get this same exact radius from the Fresnel zone. And this is a nice result and important because it tells you how to construct various things, like, for example, this next object, which is called the Fresnel zone plate. Okay, so what is the Fresnel zone plate? Well, so far we've been taking just the aperture as it is given to us, and we've been looking at how many Fresnel zones fit inside that aperture. But this very cool idea came about that what if you allow the light to go through the first Fresnel zone but block the second Fresnel zone? Okay, well, remember that the adjacent zones are pi out of phase with each other. So we're blocking the light that goes through the second Fresnel zone, but allowing the first, the third, the fifth, the seventh, etc. This is a 16-zone Fresnel plate. You can see that the total intensity now adds up in sum with each other, or the total field adds up together. There's no destructive interference between adjacent zones that is going on. Okay, so in fact, this idea of like altering the, of course, you can block it using the amplitude, or as we'll show, there's another type which is called a phase plate, where instead of like blocking the light completely, I just shift this phase here by pi. So because normally this one and this one are pi out of phase, if I additionally shift the phase here by pi, now these two become again in phase as well. So that's the second way in which one can make a Fresnel zone plate. Okay, so all right, I already mentioned this. So we can get a tremendous increase of the intensity now because usually the successive zones cancel each other out. And so you can like greatly, and in this 16-zone plate, now we get, every adjacent, the A2, A4, A6, etc. are missing because they're blocked. And instead you get A1 plus A3 plus A5 plus A7, 9, 11, A13, A15. And each of these A3, etc., they're almost approximately the same as the first Fresnel zone. Not exactly due to the obliquity factor, but roughly speaking. And therefore, we can add them up together. You see that this gives you 1, 2, 3, 4, 5, 6, 7, 8. 8 times the intensity from the first, 8 times the amplitude from the first Fresnel zone, which means total intensity now is the square of that. right? So that's 64 times the intensity from the first Fresnel zone. Okay, and then of course 64, and of course compared to the unobstructed wavefront, you could, if it's a plane wave, of course, then it's just 64 times the intensity of that first Fresnel zone, because it's a plane wave and it doesn't go off as half. Anyway, so okay, so what is the use of this? Actually, there's a very interesting use of the Fresnel zone plate, which is that we can make a Fresnel zone plate function like a lens. Okay, how does this work? Well, suppose we have a wave. So normally the unobstructed wave would go from the point S to the point P using this distance rho naught and R naught. But now by construction, what we have done is we have made sure that the wave that travels from S to P along this other path, right, differs from this path going from S to P by the distance lambda over 2, or m lambda over 2 in this case for the mth Fresnel zone. Okay, so what I'm saying is rho m plus Rm minus the distance from the direct path must be m lambda over 2. Okay, and this distance now, this rho m plus Rm minus rho naught plus R naught equals m lambda over 2. Now I'm going to use Pythagoras theorem, and I'm going to just expand out what rho m is. Well, you know, the radius of the nth Fresnel zone is Rm, and therefore rho m is just, you know, rho naught squared plus Rm squared. Similarly, Rm is that value. And now we do our usual trick. We expand using the binomial theorem, and we get rho m is equal to almost rho naught plus this factor, Rm squared by 2 rho naught. Similarly, R naught, I substitute that back there. I'm going to get cancellation of rho naught and R naught. So very straightforwardly, you can derive that 1 over rho naught plus 1 over R naught equals m lambda over Rm squared. Well, this should be familiar to you from your geometrical optics. This, if I call this value 1 over f, a focal length, well, this is saying that 1 over the object distance plus 1 over the image distance equals 1 over f, where f is now the focal length of Rm squared divided by m lambda. Okay, so this focal length, which is the first focal length as we call it, and I'll explain why in a minute, is just given by the radius of the mth zone divided by m lambda. So if I tell you whatever, 16 zones or whatever, you just divide out the 16 over there. Okay. Okay, so why is this useful? Well, of course, for a regular laser light, we have lenses, right? So and what are lenses? Basically, as you know, they are these objects that basically change the path length, the optical path length in such a way to conform with Fermat's principle, such that all the rays starting from the object reach the image point, okay, at the same time, using Fermat's principle, or have the same optical path length from the object to the image point. So for that, you need to have some kind of bending of the rays, right? You need to be able to bend the rays from the light. And there are many rays where it's wavelengths where it's difficult to find a material which does that, which has a refractive index and is transparent to the material, to the wavelengths of the light. Examples being things like X-rays and alpha particles and gamma rays and so on. All of these are electrons. Even electrons, of course, we can manipulate them with electric and magnetic fields, but maybe high energy particles of some type that you don't have that ability. But you can always probably find, like say, a metal or something else that will block some of that radiation, and you can pattern the metal at the right pattern with the Fresnel zone plate to make your lens, basically. Okay. So let us look at that. So let's imagine we have some stream of, let's say in this case, plane waves coming in, and of course then rho naught will go to 0. So that will just send off one part of that to rho naught will go to infinity. So 1 over rho naught will go to 0. And what we see now is that the Fresnel zone plate, what it does is it creates these converging waves, right? Which is just what the Fresnel diffraction does, which are going to get imaged onto this point. So that's the first focal length over here. But we should note that because Fresnel diffraction by its nature also has waves that are going off in all directions, right? That's what diffraction does. So there will also be diverging waves, which are depicted here. And there will be similarly a virtual image formed exactly at the same distance f1 behind the zone plate. Okay, so that's one difference from a regular lens, from the Fresnel zone plate to a regular lens. And now what will happen is as I move, so now imagine I was sitting here and observing the intensity, and I start moving towards the zone plate. Okay, and let's say I move a distance which is now at the distance f1 over 2. Okay, by construction, now instead of seeing one zone in every or one Fresnel zone in each of these obstructions or transparent regions, whatever you want to call them, now I'm going to see two, right? Because the Fresnel zone is just directly constructed by taking the spheres of radius lambda over 2, 2 lambda over 2, 3 lambda over 2. But if I move a distance f1 over 2, now instead of seeing one Fresnel zone in that area, I'm going to see two. Okay, so this means that two half-period zones now exist within each ring of that plate, which means now I get a minimum because those two will cancel each other out. Okay, and similarly, if I went one more distance to f1 over 3 now I have three half-period zones. That's now a maximum again. So what I observe as I go towards the zone plate, this is the maximum distance at which I'm going to observe focusing, f1. Okay, beyond this, I don't get the focusing of the waves. Okay, but if I go closer, there are successive foci that occur. So at f1 over 2, I get another foci. F1 over 2, I get destructive interference. F1 over 3, I get constructive interference, so I get another focal length. F1 over 4, I'm going to get destructive. F1 over 5, I'm going to get constructive, so on and so forth. Of course, those will be weaker compared to this primary focal length. Okay, and I already mentioned the phase reversal plate, which was suggested by Raleigh and first constructed by R.W. Wood. Instead of blocking out the even zones, he made a transparent plate, as I've already said, with slightly different thickness. So the phases now differ by pi from the adjacent zones. So instead of blocking it, you can just make the phase difference slightly different, which is pi. And that you can do, for example, by altering the thickness of the plate, right? Because then the wave has to travel a little extra distance, which will be enough to give you the phase difference of pi, for example. Obviously, that needs to be very carefully machined and so on. So that it's not easy to make it, but he was able to do this. Okay, so that's the Fresnel zone plate. So let's do a simple example, hopefully. We want to make a Fresnel zone plate with a principal focal length of 2.0 meters for laser light with a wavelength of 647 nanometers. How big should the central transparent disk be? And if it has 30 transparent regions, what's the minimum diameter of the plate? Okay, this is fairly straightforward, so I'll just quickly run through it. So R1 is just square root, hard time, times R naught lambda. So there's an M here, but M is equal to 1 for the first Fresnel zone. And R naught now, we want that to be the focal length, right? Because that's where the first Fresnel zone, we want the distance to this point to be such that it's a bright point. Okay. So this is just then simply equal to square root 2 meters times 647. Having a hard time writing here. So times 10 minus 9. Okay, very hard. Okay, so hopefully you understood that. And so you can just calculate that. I'll let you finish the calculation. And then for the 30 transparent regions, what's the minimum diameter of the plate? How would I find it how would I find the diameter if I told you that there were 30 regions instead of just one? What should be the radius or the diameter of that? Should go back further. Pascals. Let's do it. Help out your instructor. Okay, what's the question? So if I have a disk now, zone plate with like 30 of these regions, 30 Fresnel zones, basically. then what should be the radius of that plane? I just did for the first zone. So if I have 30 zones, then what happens?
Square root of 30.
Exactly. Square root of 30 times the answer from that previous calculation. Okay, so hopefully that's clear. I'm not going to attempt even to write square root of 30 with my trackpad. I tried to find the mouse right before I came. Okay, so that's it for the Fresnel zone plate. So now I want to talk about rectangular apertures. So the idea for the rectangular apertures is very similar to what we did for in the Fraunhofer diffraction. It was the circular apertures that were harder to handle, and the rectangular apertures were a little easier to handle. Whereas in the Fresnel zone, in the Fresnel picture, the spherical or circular apertures are a little easier to handle with the Fresnel zone construction. And it turns out to be the rectangular or other shape of apertures that are slightly harder to handle, and you have to use the integrals to calculate. But so the basic idea is, again, we follow the Fresnel, Huygens Fresnel principle. We have, again, our primary wavefront that's coming in to this point over here, and then it's emitting a secondary wave. And that secondary wave, of course, is now given by K of theta, which is the obliquity factor, times E naught, which is just the incident, which is the primary wavefront divided by the distance rho, right? That's the distance to the point A. And then that, since it emits a second wave, that distance 1 over r shows up in the amplitude as well. And then, of course, we need to multiply by the wave, which is cosine k times rho plus r, but that's the total phase from the source to the point P minus omega t, and then, of course, multiplied by the area of this small element here. We have chosen the aperture to lie in the YZ plane. And so, for example, for this rectangular aperture, the coordinates are y1 to y2 and z1 to z2. Okay, then it's fairly, I move into the complex notation for the wavefront because that makes it a little easier to understand. So, this is the phasor rather than the actual amplitude of the wave. So the phasor is just E naught e to the minus I omega t. And now in the denominator, you'll notice I replace rho and r by rho naught r naught. That's because basically if the dimensions d of this aperture are small compared to rho naught and r naught, and we are far, and so we can then basically say that the amplitude doesn't vary much over the aperture, but the phase, of course, is important because, as we have said, the phase is multiplied by k e to the ik, where k is 2 pi over lambda. So any deviations from the rho naught and r naught in the phase matter a lot because those are cosine or sine functions. So we have to worry about those. So we keep the rho and r as they are here, but in the denominator we replace rho and r by rho naught r naught. So that's just some constant, and that'll be just fixed by basically the by the source strength and so on. And of course, when you do this calculation for dimensions d much lesser than rho and r naught, then also the obliquity factor will be approximately 1 in this case. Okay, so we have to do this integral. So to do that, we make again using just these coordinates x. So the point A lies in the YZ plane, so it has coordinates rho naught y comma z. So I write rho as just rho naught squared plus y squared, and r as just r naught squared plus y squared plus z squared, and then we can just expand those again using binomial theorem, and we can just get this term over here. So you'll notice here that this distance rho plus r, which we care about in the phase here, is dependent on y and z through y squared plus z squared. So now it's dependent on the square of the coordinate, whereas in the Fraunhofer diffraction limit, it was dependent just on the linear parts, y and z of the aperture variables. And so we have to, we have to find out what happens to these terms. And again, this rho naught plus r naught is just a constant, so I can take it out of that integral. Oops. And the term that I'm mostly caring about in the phase is either y squared times rho naught plus r naught by 2 rho r naught, or z squared times rho naught plus r naught by 2 rho r naught. Those are the two terms. And to make this integrals easier to understand, we move to a dimensionless parameter, u and v. And what we're going to do is basically, if you look at this phase over here, it's k times rho, right? k times rho plus r, and rho plus r, as I've just said, has two terms, y squared times this factor here times k. So that's 2 pi over lambda times this y squared times rho naught plus r naught by 2 rho r naught r naught. So what I do is just replace that whole thing by a new variable u. Okay, so if you square u over here, okay, you square u, you get exactly k times, well, up to a factor of pi, you get basically k equals u squared, sorry, k times rho gives me u squared, basically, over here, back here. So this part here times this part here multiplied by k is equal to, so multiply these two terms together, if I did that, will be equal to pi times u squared. So, okay, so it's just a transformation of coordinates, basically. Okay, and same with the z part, v is just the same thing. So when I do all that, I get exactly what I just said, which is pi u squared. Oh, and there's a factor of 2. Okay, fine. But other than that, it's exactly the same. Okay, so everything in that previous integral has now been written in terms of this new variable u. Similarly with v, of course, you should verify for yourself that du and dv are exactly the same as dy and dv, except for some factors. And that's all unimportant, can be absorbed into the amplitude, for example. Okay, so at this point, what do I want to say here? Well, okay, so now you see everything up to here is just the same as a wave that went straight from the source to the point P, but then this part over here modifies the amplitude of the field. Okay, so Fresnel, these are called the Fresnel integrals. Well, I mean, as you can see, this is the complex version of those Fresnel integrals. And the Fresnel integrals are basically 0 to w cosine pi w prime squared or pi x squared over 2 dx. And similarly, the sine Fresnel integral is sine of pi w prime squared or pi x squared over 2 times dx. Okay, and this is taken from some limits from 0 to w. So you can see w is a parameter in which the this integral will be calculated. Okay, and therefore integral from 0 to w e to the I, etc., is the cosine integral plus I times the sine integral. Okay. These functions have been tabulated previously. People actually calculated these values for every imaginable value of w, right? So this w, they varied w, calculated what the cosine integral was, varied w, they did this by hand back in those days, right? They actually calculated these integrals by hand and tabulated them. Nowadays with modern computers, you can do these numerically and get the answer in like fractions of a second. And that's basically the plots of the cosine and the sine integrals, the Fresnel integral. Now, so yeah, that's all there is to it. They're just some numerical integrals and you have to do them and you get the answers. And as you can see, they sort of like, oscillate around some mean value of half and converge to that value as w goes to infinity. Okay, so this becomes half as w goes to infinity. But you can see there are some substantial deviations, and you can see the sine and cosine are out of phase. I mean, not exactly by pi over 2, but something along those lines. Okay, so there's some phase difference between them. Okay, so how do I use these? Oh, and one last thing which you should bear in mind at all times is that these Fresnel integrals are odd functions of w. Okay, and you can prove that, for example, by just switching w to minus w, right? You switch the minus sign over here, okay? But now to transform it back to the original coordinates, I would set w prime equals to minus w. So dw prime will be minus dw, okay? But in the Fresnel function, in the integrand, setting w prime to minus w brings it back to just cosine pi w prime squared, because this is a square of that variable. So again, overall, you get a minus sign. So you get that the cosine of minus w equals minus cosine of w. So that's an odd function of the coordinate w. That's why I only plot it for the positive values of w, and the negative values will just be the negative of that. Okay, that's the cosine and sine. Both of them are odd functions. Okay, and now this integral, as you can see, is very straightforward in terms of these Fresnel integrals. So this one is just the cosine plus I sine the Fresnel integral in U. This is the cosine plus the I sine Fresnel integral in V, evaluated at these two values, U1 and U2. Remember, looking back, what are U and V? Well, in fact, for like plane waves, as we'll see, this can be very simple things. They're just 2 divided by lambda R naught, where R naught is the distance to the slit. I'll show you that formula in a second. But basically, if I give you the distance from the source, distance from the slit, and then tell you what is the size of the slit, then you can just simply calculate what the limits U and V are. And I'll do an example in a minute. Okay. So let me just come back to this. But here is the plane wave approximation. So if the incoming waves are plane waves, rho naught goes to infinity, then U is just this formula over here. V is just this formula over here. Okay. And then the total electric field at the point P can be just found by calculating the magnitude squared of each of these terms in this phasor over here, and that will be just this guy over here. Okay, so you can see that this is cosine U2 minus cosine U1. That's the real part squared plus the imaginary part squared. Similarly, cosine V2 minus V1, the squared plus the real part of V and the imaginary part of the V integrals squared. Okay. So that gives us the answer. So really at this point, you can calculate it for any point that you want, but I'll just do an example to show you how to do this. So if I keep so how do I find it for anything that's not on the axis? So far I've been calculating this Fresnel integral right on the axis. So if I go back a couple slides, yeah. So I've been keeping P fixed at the center point between S to the aperture to the point P. So P is directly opposite the center of the aperture. And everything I wrote just now was for that case only. Okay. These integrals and so on are valid for that case because then everything becomes nicely symmetric around in terms of the origin and all that. But if I move this P off to the left or to the right a little bit, well, we use the same trick that we did for the circular aperture, which is instead of like moving the point P, we keep the point P fixed and we move the aperture slightly. Okay, obviously we have to reverse the direction. So if you want to go to the left in the image plane or the observation plane, we'll move the aperture to the right in the aperture plane to calculate the new limit. So we just change the limits of the integration whenever we want to calculate points off the central point. Okay, so if I move to the left a little bit, then the coordinate in this direction will become a little smaller, and the coordinate in that direction, the end limit, the limit of those integrals, this one will be a little smaller, and this one will be a little bigger, for example. If I move off all the way into the shadow of the aperture, then both of these will be positive. The limits of the integration will be positive, and there'll be no negative term to the limit of the integral. Okay, again, with an example, hopefully, I'll be able to show this to you in the next few minutes. Okay. So let's do that. Okay, so a square hole of 2 millimeters by 2 millimeters is illuminated by the plane waves of 500 nanometer light. Point of observation P is 4 meters beyond the screen, directly opposite the center of the aperture. Find the irradiance at P in terms of the unobstructed irradiance. Okay, so we have that formula for the irradiance. And so now we need to find the U1 and U2. Okay, so U1 is, I'm going to use the formula. So if I go back here, so it's just y times 2 over lambda r naught to the power to the square root. So that's just a square root, and everything is known here. The y's are just simply the distance to the edge of the slit. So if I set up my coordinates at the center of the slit, the left edge of the slit is minus 1 millimeters. So that's minus 1 millimeter. Just going to write millimeter here. Times square root 2 divided by R naught, 4 times 500 nanometers. Okay. So the answer here, which I've previously worked out, is just minus 1. Okay, so remember this is dimensionless, so everything cancels here. This is 4 meters, nanometers, that's meters on the top. So this is just a dimensionless parameter, so it's -1. Similarly, U2 will be +1, right? Because that's the positive edge of the slit from the center. And V1 and V2 will also be -1 and +1. Okay, so obviously this is set up very nicely to make it a little easier to look at the answer, but I'll explain how to do non-nice cases in a second. Okay. Okay, so what do we do? Well, of course, graphically, what we would do is we would find the point where W equals 1, right? Over here. So this is probably in between these two, right? Is 0.9. So 1 is roughly over here. So I could look at this graph, go up here, and I would expect that my value for the cosine integral is roughly 0.8, 0.78 or something like that. And for the sine integral is almost 0.4. Okay. Well, if you go look in the tables of the Fresnel integral, you find for values of the parameter 1, cosine integral is 0.78 approximately, and the sine integral is 0.44. Okay, so roughly exactly what we see from this graph. So that's it. The answer is then the intensity can simply be found by calculating. And obviously since this is a so cosine of 1 for the U2 is equal to minus cosine of -1, right? Because it's an odd function. So then when I take cosine of 1 minus cosine of -1, which is what this formula here says to do, right? Cosine of U2 minus cosine of U1, that's just twice the cosine from any one of them. Right, so that term will just be 2 times that. So the intensity, I'm not going to do the numbers. So the intensity is just simply obtained as twice this value of 0.8, which I got from here, the whole squared, plus similarly for the sine case, and then of course I also have to do for the other situation, which is for the this is just for one coordinate from U, which is say in the y plane, in the y-axis, and then similarly I have to do the z-axis. Okay, so that was for the case where the point of observation is exactly opposite to the center of the aperture. Is that clear to everyone? How I got these values and how to plug them into that formula? What to do? It's not. I mean, again, as I said, all I'm doing is calculating the C of U2, C of U1. S of U2, S of U1, that's for what I just did here. And I'm just saying C of U2 is equal to minus C of U. Therefore, these two are just adding up together. Same with this function. And then I had to do that for also the V case, which is the Z direction. Okay, so that's then plugged in and you obtain the intensity, whatever that number is. Okay, using these values for the cosine and the sine integral. Okay. Now what will happen if I move off the screen? Well, that's actually going to be a little easier to see. You can do it. Basically, if I move a little bit to the left, like I was describing in the earlier situation, now my y1, let's say, goes to minus 0.8. So it's a 20% change in the limit of the integration. Okay. So if y1 goes as minus 0.8, meaning I moved a little bit to the left, so that now the y1 term in this aperture, if I show you the drawing, maybe that will become, yeah, right here. So if I move to the left over here, so then the limit of the integration, instead of being earlier minus 1, is going to become, say, minus 0.8. Okay, that the y1 coordinate will be minus 0.8, and the y2 coordinate will be, say, a little bit higher, 1.2, right? Because as I said, moving to the left here is equivalent to moving the screen to the right. Okay, so therefore it's the same idea. So instead of like calculating the trying to find out what this distance is, we just move the screen to the right by the same amount, which is now going to change the limits of the integration. So now y1 will be minus 0.8, which means then u1, again, if I plug in minus 0.8 up here, this is, remember, the y1 over here, I'll get also minus 0.8. And then U2 will be 1.2. Okay, so that just means that instead of finding the value for the cosine integral at exactly 1.0, I need two values, one at 0.8 and one at 1.2. And so now it will no longer just be twice the values, but I have to actually find these two values and find the difference and square that to get the intensity now. Okay, so that's the numerical procedure, but it turns out there's a much nicer graphical procedure which was invented by Marie Cornu. And I think this is a nice procedure because it gives us some intuition for what's going on with the intensity. Okay, so to understand this construction in the next couple minutes, hopefully I can get through this. What we need to know is that we're plotting in the complex plane the phasor C of W plus I S of W. So in this plane, this is coordinate is given by C, the cosine Fresnel integral, and in this coordinate, the sine Fresnel integral. Okay. Then it turns out that if I plotted the values of each of the Fresnel integrals for different values of W as shown here, it'll be along this spiral. Okay, and there's a more physical reason for that, but I don't have time to get into that today. Okay. So the arc length along the curve, what I mean by arc length is if I give you W, remember W comes from the dimensions of the slit. If I give you W, that is just equal to this arc length along the curve as shown by this proof here. So I take the first element dc squared plus ds squared. dc squared is just the differential of that integral for the Fresnel integral. That's just cos squared pi w squared over 2. Similarly, ds squared is just sine squared pi w squared over 2 times dw squared. So I get dl, the arc length, is equal to dw. So what this means is, if I just give you a value of w, from which you can do by just calculating the boundary of the slit, and those values are marked off here. Let's say I had 0.5 over here for the coordinate for the edge of the slit. Then I just go along the curve until I hit this 0.5, or if it was say 1, which is what our case was for the previous slit, we go up to 1. Similarly, we can go to minus 1. Oops, sorry. Similarly, I can go to minus 1. And now the answer is basically given by taking the phasor between these 2 points and finding the magnitude square of that. So this is the nice result from Cornu spiral. One more thing to note is that any point, say W here, makes an angle with respect to the tangent to the curve makes an angle, which I proved down below. That value is just pi w squared over 2 as well. And that's just a result from the math. So that's another way to find what that angle at which this phasor is going to be at. But anyway, so the point is that the result intensity is just taken by taking this phasor and squaring it. Okay. So now what happens if I move the value of if I move the slit to the left away, as we just did by the amount 0.2, which is, so now let me change the color if I can. Let's call it blue. So now instead of going to the point minus 1, I'll be going to the point minus 0.8, like I just did on that previous example. And up here, I'll be going to the point 1.2 over here. So this was 1.0, this was 1.1, and this is 1.2 over here. And now I'll draw the phasor from this point to here, right? Because all that changed is the endpoints of the integration. The length of the arc cannot change because the length of the arc is basically determined by the size of the slit. So the size of the slit fixes how long this arc is, which is, you can think of it like a piece of string that's lying between the points minus 1 to 1 initially. And then as I move my observation point to the left, that just makes the the strings slide along the Cornu spiral towards the right. So it goes up to this minus 0.8 here and then 1.2 over here. So there's imagine the piece of string just sliding up along the Cornu spiral, and that changes the length of this phasor over here. You can see as I keep moving my observation point to the left, this phasor will start to, as I slide the string, basically one end of the string will start to spiral around. Okay. Eventually, as you can see, this string will get looped further and further around the spiral, so that, for example, if I'm very far to the left, say one of the endpoints will be here and the other endpoint could be here. And so now my phasor will be much smaller. So I start to get lesser and lesser intensity as I slide further and further to the left on my observation, or further to further on the right on the slit. And also you can see there'll be fringes. For example, at some point, the length might be here, and then as it gets over here, it might go smaller and bigger and so on. Okay, so hopefully the intuition is there for like why we are getting fringes from just looking at the endpoints of this phasor. Okay, so I'm out of time, and we have a couple questions to get through. I'm going to post a little video on like other examples with the Cornu spiral, because I think it's a nice physical way to do this. So I'll post that video, and then I'm happy to answer any questions as well in the review session if you like. Okay, so let me stop this.